Hey there, welcome back. My name is Liam, and this is Deep Space Intelligence, the channel where we dig deep into the universe's biggest mysteries, armed with the best science we have and a genuine commitment to following the evidence wherever it leads. If you are new here, I am glad you found us. If you have been with us for a while, thank you truly for coming back. Today we have something remarkable on our hands. Something that honestly stopped me in my tracks the moment I began researching it. Because what the James Webb Space Telescope has now given us is not just another beautiful image of a distant galaxy, or another incremental data point nudging our models in a slightly new direction. What Webb has given us is a confrontation, a direct, unavoidable, scientifically documented confrontation with something that our best theories of the universe say simply should not be there. And I want to be very clear about something from the start. This is not hype. This is not the kind of sensationalism you might find on other platforms. The challenge that Webb is presenting to our cosmological models is real. It is peer-reviewed. It is being actively debated by some of the most brilliant minds in physics and astronomy today, and it has genuine implications for how we understand the very shape, age, and history of everything that exists. So let us begin at the beginning, because to fully appreciate why this discovery is so unsettling, you first need to understand what we thought we knew, and how carefully, over the course of nearly a century, we constructed the framework that these new observations are now testing. For roughly 100 years, cosmology has been built on a single, elegant, and deeply reassuring assumption. It is called the cosmological principle, and it states, in essence, that the universe is the same everywhere, that no region of space is fundamentally special, and that when you zoom out far enough, matter is distributed smoothly and uniformly in every direction you look. This idea did not come from nowhere. It has deep philosophical roots going back to the Copernican revolution of the 16th century, that pivotal moment in human intellectual history, when we accepted that Earth is not the centre of the solar system, that we are not the focal point of creation, and that by extension, we do not occupy any privileged location in the cosmos. The cosmological principle is the mathematical formalization of that humility, extended to its logical conclusion. We are not special. Our galaxy is not special. Our neighbourhood of the universe is not special. And the universe, on the grandest scales we can imagine, is a remarkably smooth, isotropic, uniform place. This principle underpins the Lambda cold dark matter model, which cosmologists abbreviate as Lambda CDM. That model is the standard model of cosmology, the accepted framework that describes how the universe began with the Big Bang approximately 13.8 billion years ago, how it evolved through successive epochs of plasma, recombination, and structure formation, and how the remarkable complexity we observe today, including the galaxies, galaxy clusters, and vast filaments of the cosmic web, came to emerge from an initially almost perfectly uniform sea of matter and radiation. And Lambda CDM has been extraordinarily successful over the decades of its development and refinement. It has made predictions that were later confirmed by independent observation. It has explained, with remarkable precision, the temperature fluctuations in the cosmic microwave background, the faint thermal afterglow of the Big Bang that permeates the entire sky. It has accurately predicted the relative abundances of light elements like hydrogen, helium, and lithium, produced in the first few minutes after the Big Bang. It has described the large-scale clustering of galaxies in excellent agreement with what massive sky surveys have catalogued. But there is a boundary built into the cosmological principle, a hard physical ceiling that follows directly from combining the principle of homogeneity with the known age and expansion history of the universe. Because if the cosmos is truly uniform on large scales, then structures within it, things like galaxy clusters and superclusters, and the immense filaments that connect them, can only grow so large. Matter requires time to gravitationally assemble itself into coherent structures. The larger the structure, the longer it takes to form, and the universe has only been around for about 13.8 billion years. Cosmologists have calculated carefully and rigorously, using the mathematics of gravitational collapse within the standard framework, that any individual structure in the universe should be no larger than roughly 1.2 billion light-years across. That is the theoretical size limit dictated by the cosmological principle and the age of the cosmos. Beyond that threshold, a structure would be so vast that it could not have assembled itself through ordinary gravitational processes in the available time since the Big Bang. It would represent, in the precise language of physicists, a violation of the cosmological principle. Now pause on that number for a moment. 1.2 billion light-years. That is already a distance so vast as to border on the meaningless to human intuition. A single light-year is the distance light travels in 1 year at nearly 300,000 kilometers per second, and that alone works out to roughly 9.5 trillion kilometers. 1 billion light-years is 1 trillion times that. The very fact that we can even speak meaningfully about structures on this scale is a testament to the extraordinary power of modern telescopes, sky surveys, and the mathematics of general relativity that allows us to translate observed redshifts into cosmic distances. For decades, despite the steady discovery of increasingly large cosmic features, the cosmological principle held its ground. The biggest things we found seemed more or less to respect the theoretical limit. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, stretches about 1.37 billion light-years and already pushed at the edges of what the model allows. The South Pole Wall, mapped in 2020, is comparable in scale. These were anomalies, wrinkles in the otherwise smooth picture, but they were not decisive violations. They occupied a range where statistical uncertainty and observational limitations could still plausibly stretch to account for the discrepancy. Then came Webb, and then came a cascade of discoveries that has fundamentally shifted the conversation about the universe's structure, its history, and whether our most cherished model of cosmology is fully correct. Before we get into the specific structures that Webb and related observations have brought into focus, it is worth understanding exactly what this telescope is and why it represents such a qualitative leap forward in our ability to observe the cosmos. The James Webb Space Telescope was launched on the 25th of December 2021, a date that will likely stand as a turning point in the history of astronomy. It began its full scientific operations in mid-2022 after a careful and painstaking commissioning process, and it is not, it must be emphasized, merely an upgraded version of its predecessor, the Hubble Space Telescope. It is a fundamentally different kind of instrument, designed from the ground up to answer questions that Hubble could not even formulate, let alone answer. While Hubble observes primarily in visible and ultraviolet light, Webb was designed to peer at the universe in infrared wavelengths, from near-infrared through mid-infrared. That distinction matters enormously for the study of the early universe. As space expands, the light from distant objects gets stretched along with it. The farther away a galaxy is, the more its emitted light has been redshifted, meaning its wavelengths have been stretched toward the red end of the electromagnetic spectrum and beyond, into infrared territory. The most ancient galaxies, those that formed just a few 100 million years after the Big Bang, emit light so heavily redshifted that it arrives at Earth in the infrared band, utterly invisible to an optical telescope like Hubble. Webb was built specifically to detect this ancient stretched light. Its primary mirror spans 6.5 meters in diameter, assembled from 18 hexagonal gold-coated beryllium segments that unfurled in space like a mechanical flower. This makes it nearly 3 times the collecting area of Hubble's mirror. It operates from a gravitationally stable location called the second Sun-Earth Lagrange point, about 1.5 million kilometers from Earth, always pointing away from the Sun, bathed in deep shadow behind its 5-layered sunshield the size of a tennis court. That sunshield is not decorative. Webb's infrared detectors are so sensitive that even the faint warmth of its own structure could overwhelm them with noise. The sunshield reduces the temperature on the cold side of the telescope from roughly 85 degrees Celsius to negative 233 degrees Celsius, just 40 degrees above absolute zero. In that extraordinary cold, Webb can detect infrared photons from galaxies more than 13 billion light-years away. The result is that Webb can look back in time further than any telescope in human history. When Webb stares into a patch of seemingly empty darkness, it is not merely peering across vast distances of space, it is peering across vast stretches of time itself. Light from the most distant galaxies Webb has detected has been travelling for over 13 billion years to reach its detectors. What the telescope captures is a genuine snapshot of the infant universe, a window into the cosmic dawn when the very first stars ignited and the very first galaxies coalesced from the primordial hydrogen and helium gas. And what Webb has seen in that window has not matched what we expected to find. Not by a small margin, not in ways easily explained by measurement error, but in ways that are systematic, reproducible, and scientifically significant. Let us begin with the individual galaxies, because the story of anomalous cosmic structure starts with the basic building blocks. One of the most celebrated and discussed early discoveries from Webb was a galaxy now known as JADES-GS-Z14-O. The name derives from the JWST Advanced Deep Extragalactic Survey, the ambitious program designed to study the most distant and earliest galaxies ever observed, conducted using guaranteed observing time on Webb in its first operational cycle. The discovery was the result of both deep photometric imaging and, crucially, spectroscopic confirmation. In October 2023, the JADES team conducted an extraordinarily deep imaging campaign, devoting 5 full days of Webb's near-infrared camera to a single patch of sky in the direction of the constellation Fornax, creating what they called the JADES Origins Field. And then, in January 2024, the near-infrared spectrograph observed JADES-GS-Z14-O for nearly 10 hours, collecting enough photons to produce a definitive spectrum. When the data were analysed, the result was staggering. The galaxy has a redshift of 14.32, with a measurement uncertainty of just 0.08 on the high side. In cosmological terms, this places the galaxy at a moment in the history of the universe fewer than 300 million years after the Big Bang, when the cosmos was only about 2% of its current age. Kevin Hainline, an associate research professor at the Steward Observatory at the University of Arizona, and one of the lead authors of the study, described the moment when the spectrum was first processed in the following terms. There was, he said, unambiguous evidence that the galaxy was at a redshift of 14.32, shattering the previous record. Stefano Carniani of the Scuola Normale Superiore in Italy was the other lead author, and the two researchers, along with their international team, published the result in May 2024. But the record-breaking distance was only one part of the story. What made JADES-GS-Z14-O scientifically extraordinary was its size and brightness. Webb measured the galaxy at more than 1,600 light-years in diameter. It is, by the standards of galaxies at this epoch, genuinely large. Many of the most luminous objects in the early universe, including a class of objects called quasars, produce their light through the violent process of matter falling into a supermassive black hole at their centre, a process that can outshine an entire galaxy of hundreds of billions of stars. But the spatial extent and spectral properties of JADES-GS-Z14-O led the research team to conclude that its light is being produced primarily by young stars, not by an active central black hole. This is significant because it means the galaxy was not a quasar in disguise. It was a genuine stellar system, forming stars at a prodigious rate, already several hundred million solar masses in total stellar content, less than 300 million years after the universe began. Then, in March 2025, astronomers using the Atacama Large Millimeter Wave and Submillimeter Array in the high-altitude desert of northern Chile announced that they had detected oxygen in JADES-GS-Z14-O, a discovery reported across the astrophysical community as the most distant detection of this element to date. Oxygen is a heavy element in the cosmological sense, meaning it is not primordial. It cannot be produced in the Big Bang, which generated only hydrogen, helium, and trace amounts of lithium. Oxygen must be forged in the nuclear furnaces of stellar cores through the fusion of carbon and helium in the final stages of a massive star's life. And when those massive stars exhaust their nuclear fuel and die in titanic supernova explosions, they scatter the oxygen and other heavy elements they have synthesized back into the interstellar medium, where future generations of stars and planets can incorporate it. For oxygen to be present in a detectable quantity in JADES-GS-Z14-O, generations of stars must have already been born, lived their entire lives and died, and their chemical legacy must have been absorbed into the surrounding gas, all within the first few 100 million years after the Big Bang. The detection of oxygen also allowed astronomers to precisely refine the galaxy's distance measurement, reducing the uncertainty to just 0.005%, making it one of the most precisely placed objects in the early universe. The University of California Santa Cruz team, led by Brant Robertson, and the Cambridge team led by Sandro Ticella, were among those involved in the broader JWST analysis that provided context for this galaxy. Their assessment, shared in multiple publications, was that the age, size, and luminosity of JWST-GS-Z 14-0 added to a growing body of evidence that current theories of early star and galaxy formation are incomplete. That is a precise and careful statement. Incomplete. Not wrong, not shattered, not disproven, but incomplete. And when theories that have been as precisely tested and widely confirmed as Lambda CDM are described as incomplete by the people who know them best, it is worth paying serious attention. JADES-GS-Z 14-0 is not alone in its anomalousness, not remotely. Webb has now produced data on dozens of similarly unexpected galaxies at high redshift, objects that are more massive, more luminous, and more chemically evolved than the standard model says they should be at their respective epochs. A landmark study published in 2022 by Ivo Labbe at the Swinburne University of Technology in Australia, and colleagues, using Webb's very first release science images from the Cosmic Evolution Early Release Science Program, identified several galaxy candidates at redshifts between 7 and 10, roughly 700 million to 500 million years after the Big Bang, with implied stellar masses of up to 10 billion solar masses. To put that in context, the Milky Way today contains somewhere between 50 and 60 billion solar masses of stars accumulated over more than 13 billion years of star formation. These early JWST galaxies appear to have assembled roughly 10 to 20% of the Milky Way's current stellar content in a fraction of the time. Michael Boylan-Colchin of the University of Texas at Austin engaged with this problem directly, publishing a rigorous analysis in Nature Astronomy in 2023. He examined the fundamental physical constraint on galaxy formation in Lambda CDM. The mass of a galaxy is ultimately limited by the mass of the dark matter halo in which it forms, because dark matter provides the gravitational scaffolding that allows gas to accumulate. The total mass function of dark matter halos at any given epoch, as predicted by Lambda CDM, sets an absolute upper limit on how many galaxies above a given stellar mass can exist. Boylan-Colchin found that some of the early Webb galaxy candidates appeared to violate this limit, requiring star formation efficiencies of 100% or higher. Real star formation is notoriously inefficient. Stellar feedback, the radiation pressure and supernova explosions from newly formed stars tends to blow away the very gas that would have formed more stars. Observed star formation efficiencies in the universe today typically range from a few percent to at most 30% in the most vigorous starburst galaxies. 100% efficiency is not a stretch of the standard model. It is a violation of basic physical plausibility. Here I want to pause for a moment, because I think intellectual honesty requires it, and because I genuinely believe that one of the most valuable things this channel can do is model careful, nuanced engagement with evidence. The story of the early Webb galaxy tension has evolved as better data have come in, and some of the initial alarm has been moderated by subsequent analysis. In particular, a 2024 study using data from Webb's mid-infrared instrument, known as MIRI, conducted as part of the Primer survey and led by Tao Wang at the Nanjing University, found that previous stellar mass estimates for the most extreme early galaxies had been systematically overestimated, in some cases by as much as a factor of 2 to 3. This was because earlier measurements had lacked rest-frame near-infrared data, which MIRI can now provide for the first time. Including the MIRI data reduced the number density of the most extreme massive galaxy candidates by about 36 to 55% depending on the mass threshold. That is a genuine, important and welcome result. It means that some of the alarm was premature, and that the raw tension between early Webb data and Lambda CDM was somewhat overstated in initial reports. Science is a self-correcting process, and this is a good example of it working as it should. But even after this correction, even with the best available MIRI photometry and the most careful stellar mass modelling, an excess of massive luminous early galaxies remains. The tension has been softened but not erased. A 2026 paper from researchers at the University of California, Irvine, developing a detailed galaxy formation framework incorporating multiple sources of uncertainty, found that the most extreme early galaxy candidates in the Webb data still require baryon to stellar mass conversion efficiencies that approach or exceed physically plausible limits. The core problem persists. It has shrunk, but it has not disappeared. And as I always encourage when we discuss findings at the frontier of science, I would urge you to look into these papers directly. The JWST team publishes its results in open access journals and on the Arxiv preprint server. The Nature Astronomy analysis by Boyle and Colchin is publicly accessible. The MIRI study from the Primer survey is available to anyone with internet access. Science conducted at the frontiers of human knowledge is not a closed priesthood. It is a public conversation, and the more people who engage with it critically, the better the conversation becomes. Now, if anomalously massive individual galaxies were the only issue Webb had uncovered, the situation would be interesting but perhaps ultimately manageable within the existing framework. Theories can be adjusted, parameters can be tweaked, and with enough flexibility, even a model under stress can be made to accommodate new data. But Webb's discoveries do not stop at the scale of individual galaxies. They extend to an entirely different level of cosmic architecture, to structures so vast that no amount of parameter adjustment can make them fit comfortably within the standard model. To understand why large-scale structures pose such a fundamental challenge, we need to think about how structure forms in the universe at all, at the level of galaxy clusters, superclusters, and the immense filamentary network known as the cosmic web. In the standard Lambda CDM picture, the story begins immediately after the Big Bang, with a phase of extraordinarily rapid expansion called inflation, a brief but transformative epoch in which the universe expanded by a factor of at least 10 to the power of 26, smoothing out any large-scale irregularities while simultaneously stretching microscopic quantum fluctuations to cosmic scales. These stretched fluctuations became the seeds of all subsequent structure. When inflation ended and the universe settled into the more gradual expansion we observe today, those seeds were imprinted in the density of matter, with some regions ever so slightly denser than others. Over the next hundreds of millions of years, gravity quietly amplified those density contrasts. Slightly denser regions pulled in more matter from their surroundings, becoming denser still, while underdense regions emptied out, becoming the vast cosmic voids we map today. This process, called gravitational instability, is the engine of cosmic structure formation, and it obeys a fundamental law. Structure grows from the bottom up. Smaller scales collapse first because the density contrast reaches a critical threshold sooner in compact regions. The first objects to form were relatively modest clumps of dark matter, called halos, which later accreted gas and formed the first stars and galaxies. Over billions of years, smaller halos merged into larger ones. Galaxies gathered into groups and clusters. Clusters stretched along the filaments of the cosmic web into superclusters and great walls. It is a magnificent process, and Lambda CDM describes it with extraordinary mathematical precision, using simulations like the Millennium Simulation, the illustrious TNG project, and the Eagle simulation, all of which produce synthetic universes that closely resemble what we observe. But all of those simulations, and all of the mathematical theory underlying them, agree on the fundamental scale limit. Structure cannot grow arbitrarily large in the age of the universe. The density perturbations seeded by inflation were tiny. The universe's expansion has been working against gravitational collapse throughout cosmic history, and there simply has not been enough time for matter to organize itself into coherent structures much larger than about 1.2 billion light-years. That is not a choice, or a parameter that can easily be adjusted. It is a consequence of the underlying physics, which is why violations of this limit are so scientifically serious. Now consider what astronomers found even before Webb came into the picture. In 2021, a doctoral student named Alexia Lopez at the University of Central Lancashire in the United Kingdom was conducting research into large-scale structure using an inventive technique. Rather than mapping galaxies directly, she was tracing the distribution of intervening matter through its absorption signature in the light of distant quasars. Quasars are among the most luminous objects in the universe, the brilliant cores of active galaxies powered by supermassive black holes consuming enormous quantities of gas. Their light, travelling billions of light-years to reach us, passes through clouds of gas associated with intervening galaxies, and some of that gas contains singly ionized magnesium atoms, which absorb light at a specific predictable wavelength. By cataloguing these absorption features in large samples of quasar spectra, Lopez could effectively create a three-dimensional map of the matter distribution between us and the quasars, without needing to directly observe the galaxies themselves. What she found in the SDSS catalogue was a sweeping curved filament of matter stretching approximately 3.3 billion light-years from end to end. It was located about 9.2 billion light-years from Earth, existing at a cosmic epoch when the universe was roughly half its current age. She named it the Giant Arc. The discovery was detailed in a peer-reviewed paper published in the monthly notices of the Royal Astronomical Society in 2022, authored by Lopez along with Roger Close and Gerard Williger of the University of Louisville. The paper triggered immediate, intense scientific debate. The Giant Arc is almost 3 times larger than the 1.2 billion light-year theoretical maximum set by the cosmological principle. Lopez herself was measured and precise in her assessment of what the discovery meant. In a statement accompanying the publication, she noted that the growing number of large-scale structures exceeding the theoretical viability limit is becoming harder to ignore. She was clear that she was not claiming to have disproven cosmology, but she had identified an anomaly of genuinely significant magnitude. Then, in January 2024, at the 243rd meeting of the American Astronomical Society, Lopez presented something that elevated the mystery to an entirely different level. While continuing to analyze the same catalogue of quasar absorption data, this time using updated and expanded catalogues from the Sloan Digital Sky Survey's 16th data release, she and colleagues Close and Williger discovered a second ultra-large structure. At the same redshift, at the same cosmic distance, and in the same region of the sky as the Giant Arc, they found a ring. A nearly circular arrangement of matter with a diameter of approximately 1.3 billion light-years, located just 12 angular degrees away from the Giant Arc on the sky. They named it the Big Ring. Take a moment to appreciate the strangeness of this. A ring. Not a rough concentration, not a smeared-out overdensity, but a structure with genuine circular geometry, a 1.3 billion light-year ring of galaxy clusters and diffuse matter hanging in the cosmos, sitting right next to the Giant Arc in both distance and angular position. At the same redshift of approximately 0.8, both structures existed at the same moment in cosmic time, roughly 9.2 billion years ago. They are, in the language of cosmology, neighbours. And Lopez pointed out explicitly in her presentation that 2 such extraordinary ultra-large structures in such close configuration raises the possibility that together they form an even more extraordinary cosmological system. The peer-reviewed paper detailing the Big Ring, authored by Lopez, Close and Williger, is available on ARIV and was presented publicly at the AAS meeting in early 2024. In it, the authors describe the structure as a striking circular annulus-like formation with a diameter of approximately 400 megaparsecs in proper size at the present epoch. Its circumference, they noted, is comparable to the full length of the Giant Arc. Neither structure has a known cause within the current understanding of the universe. Neither fits comfortably within the cosmological principle, and their proximity to each other, in both cosmic time and angular position on the sky, seems unlikely to be coincidental. Lopez was admirably transparent about the limitations of the analysis. She acknowledged that where no quasar happens to lie behind a region of space, the technique cannot detect intervening matter, meaning the catalogue has gaps, and the full extent of these structures might differ from what is currently mapped. She expressed her own skepticism, noting that, like everyone, she too maintains a critical perspective on her own findings. She would, she said, love to have the answers, and she concluded, in collaboration with her co-authors, with a statement that has the measured quality of genuinely careful science. The Big Ring and the Giant Arc together, given their sizes and morphologies, are presumably telling us something intriguing and quite possibly important about the universe, but at the moment we can only speculate what that might be. There are several theoretical proposals for what the Big Ring might be. One invokes a physical phenomenon called baryon acoustic oscillations. In the early universe, before the cosmic microwave background was emitted, the primordial plasma was filled with pressure waves, oscillations driven by the competing forces of radiation pressure and gravity. These waves travelled outward at a significant fraction of the speed of light, carrying energy and redistributing matter until the universe cooled enough for hydrogen atoms to form and the plasma became transparent. At that moment, the waves were frozen in place, leaving an imprint in the distribution of matter at a preferred scale of approximately 490 million light-years in the present-day universe. This imprint, known as the Baryon Acoustic Oscillation Scale, or BAO scale, is real and has been detected in galaxy surveys. Some researchers have proposed that the Big Ring might be related to this scale, but there are difficulties with this interpretation. The BAO signal produces a statistical preference in galaxy clustering rather than a discrete geometric ring, and the Big Ring's diameter, at about 1.3 billion light-years, does not straightforwardly match the expected BAO scale. The proposal remains an open possibility, but not a settled explanation. Of all the large-scale structures that have emerged from the data to challenge the cosmological principle, none has done so with quite the scale or drama of the structure first reported by Hungarian astronomers István Horváth, Jon Hakila, and Zsolt Bagoli in 2014. To understand why their discovery was so impactful, you need to understand the nature of the cosmological beacons they used to find it. Gamma-ray bursts are the most energetic explosions in the known universe. They occur when certain massive stars collapse at the ends of their lives into black holes, producing narrow jets of particle beams and electromagnetic radiation moving at very nearly the speed of light, or when two neutron stars spiral together in a gravitational death dance and finally merge. For a fraction of a second, or at most a few minutes in the case of the long-duration variety, a single gamma-ray burst can outshine the entire observable universe across several octaves of the electromagnetic spectrum. They are visible across billions of light-years with existing detectors, and because they are the deaths of massive stars, they trace the distribution of star-forming matter throughout the cosmos. Where gamma-ray bursts happen, galaxies are present, and where galaxies cluster, structure exists. Horváth, Hakila, and Bagoli were analysing the angular distribution of gamma-ray bursts with spectroscopically confirmed redshifts, using data accumulated over years of observations by instruments, including the SWIFT satellite and the Fermi Gamma-ray Space Telescope. When they examined the spatial distribution of bursts at redshifts between 1.6 and 2.1, corresponding to a cosmic epoch roughly 9 to 10 billion years ago, they noticed an extraordinary anomaly. In the direction of the constellations Hercules and Corona Borealis, in the northern sky, gamma-ray bursts were clustering with a statistical concentration far exceeding what would be expected from a random, homogeneous distribution of matter. The clustering was not subtle, it was stark. Statistical tests gave it a probability of arising by chance in a homogeneous universe of less than 1 in a few 100,000. The structure implied by this clustering was colossal. Horváth and colleagues estimated its scale at between 2 and 3,000 megaparsecs, roughly 6 to 10 billion light-years. They named it the Hercules Corona Borealis Great Wall, and it immediately became the largest known structure in the observable universe by an enormous margin, dwarfing everything that had been catalogued before it. The Sloan Great Wall, which had held the record since 2003 at about 1.37 billion light-years, was suddenly not even remotely in the same category. The Hercules Corona Borealis Great Wall, if the initial estimates held up, was 6 to 8 times larger than the theoretical maximum allowed by the cosmological principle. The result was met with intensive scrutiny, as it deserved to be. Critics pointed out that the gamma-ray burst dataset was relatively sparse, and that the positions of individual bursts carry measurement uncertainties. Some argued that angular sampling biases, regions of sky that are difficult or impossible to observe due to galactic foreground dust, could in principle create the illusion of clustering where none truly existed. A 2016 paper by Uquata and Wozniak used kernel density estimation methods to argue that the observed anisotropies could potentially be explained by such selection effects. This was important, and the researchers took it seriously. Horváth and colleagues responded with increasingly refined statistical analyses, incorporating larger samples and more sophisticated bias corrections. A 2015 paper in Astronomy and Astrophysics used nearest neighbour tests and bootstrap point radius methods, both applied independently, and both continued to show statistically significant clustering at the same sky position and the same redshift range. The signal was robust against multiple independent lines of criticism. Then, in April 2025, a new paper authored by Horváth and an expanded collaboration was posted to the Arxiv preprint server. This analysis used an even larger and more complete gamma-ray burst catalogue than had been available in previous studies, and it reached a striking conclusion. The Hercules Corona Borealis Great Wall, they found, might be substantially larger than previously estimated. New positional constraints and a more complete redshift coverage suggested the structure could extend as far as 15 billion light-years in its longest dimension, with a thickness approaching 1 billion light-years. The science journalism site IFL Science, reporting on this paper in April 2025, described the latest dimensional estimates as 10 by 7.2 billion light-years for the main body, with a thickness of nearly 1 billion light-years. To place that thickness alone in perspective, recall that the Andromeda Galaxy, the nearest large spiral galaxy to our own Milky Way, sits at a distance of about 2.5 million light-years. The thickness of this structure would encompass that distance 500 times over. Some scientists remain appropriately cautious about the Great Wall. They note that gamma-ray burst redshift measurements are imprecise by the standards of galaxy spectroscopy, that the catalogue still has gaps and incompleteness, and that any region of space not covered by a burst could harbour structure we simply cannot see yet. These are legitimate scientific concerns and they matter, but the key point is this: the sceptical voices are not claiming the Great Wall does not exist. They are arguing that its precise dimensions are not yet definitively established. The underlying statistical signal, the anomalous concentration of gamma-ray bursts in this region of the sky, at this range of distances, has withstood a decade of increasingly sophisticated attempts to dismiss it. In science, when a result survives that kind of scrutiny and continues to strengthen with additional data, it reaches a threshold where it demands a serious theoretical response. And the theoretical responses that have been seriously proposed are, in themselves, remarkable in what they imply. Some researchers have explored whether the Hercules Corona Borealis Great Wall could be explained within an extended Lambda CDM framework by invoking a modification of the primordial power spectrum, the distribution of density fluctuations seeded by inflation. If inflation produced slightly more power at large scales than the simplest inflationary models predict, structure formation might proceed somewhat differently at those scales, potentially allowing larger coherent structures to emerge. This is a mathematically tractable proposal, but it requires introducing new parameters or a different inflationary potential with no independent observational justification. Others have turned to the idea that dark energy, the mysterious force driving the universe's accelerating expansion, may not be the simple, constant cosmological constant that Lambda CDM assumes, but something that evolves with time. If dark energy has varied in strength over the history of the cosmos, it would have altered the rate of structure growth at various epochs, potentially enabling the formation of larger than expected structures in the intermediate cosmic history period that corresponds to the redshifts where the Great Wall is observed. This connects directly to one of the deepest current crises in physics, one that the James Webb Space Telescope has played a central role in clarifying and deepening, and which we are now going to examine in full. Because beyond the specific structures Webb has revealed, and beyond the individual galaxies that should not exist, there is a tension running through the entire edifice of modern cosmology, a fault line so fundamental that it touches the rate at which the universe itself is expanding, and whether our entire mathematical description of space-time, gravity, and the content of the cosmos needs to be revised. The anomaly is called the Hubble tension, and in the words of one of the world's leading observational cosmologists, it has now become a crisis. The Hubble constant, named in honour of Edwin Hubble, who first systematically measured the recession velocities of galaxies in the 1920s and thereby established the expansion of the universe, is the fundamental parameter that quantifies how fast that expansion is proceeding today. More precisely, it expresses the relationship between a galaxy's recession speed and its distance from us. For every additional megaparsec of distance, a galaxy recedes from us by a number of additional kilometers per second equal to the Hubble constant. This constant determines the scale of the universe, its age, and the rate at which the density of matter and energy has changed over cosmic history. It is arguably the single most important number in cosmology. There are two main ways to measure it. The first is by analysing the cosmic microwave background, the ancient light emitted when the universe was only 380,000 years old, and finally cool enough for electrons and protons to combine into neutral hydrogen atoms. This thermal radiation, mapped with extraordinary precision by the European Space Agency's Planck satellite over a mission spanning from 2009 to 2013, encodes the initial conditions of the universe in its temperature fluctuations. By fitting the standard Lambda CDM model to the Planck data, cosmologists can extract all the cosmological parameters simultaneously, including the Hubble constant, which comes out at about 67.4 kilometers per second per megaparsec from this approach. The second method is to measure the expansion rate directly in the local universe, using a carefully calibrated chain of distance measurements called the cosmic distance ladder. The base of the ladder rests on Cepheid variable stars, a class of pulsating stars whose intrinsic luminosity is tightly correlated with their pulsation period. By measuring the period, astronomers can infer the luminosity, and by comparing the inferred luminosity to the observed brightness, they can determine the distance. Cepheids in nearby galaxies provide the first rungs of the ladder, anchoring the distances to those galaxies. Those distances then calibrate the luminosities of a special class of stellar explosions called Type Ia supernovae, which are bright enough to be observed across billions of light years and which appear to have a consistent peak luminosity that makes them excellent distance indicators. The JWST team, led by Adam Rees of Johns Hopkins University, has been refining this measurement for years. Their best current local measurement of the Hubble constant is approximately 73 km per second per megaparsec. These two numbers, 67.4 from the early universe and 73 from the local universe, should be the same. They are measuring the same fundamental property of the same universe using two entirely independent methods. But they disagree by approximately 9%, and 9% might sound modest, but in the world of modern precision cosmology, where measurements are routinely made to fractions of a percent, 9% is not a rounding error. It is a screaming alarm bell. Webb has been central to investigating the origin of this discrepancy. For years, one of the leading hypotheses for the local Hubble constant being high was that Hubble Space Telescope images of Cepheids in distant galaxies might have been affected by crowding, the blending of multiple closely packed stars into what appeared to be a single brighter star. If nearby fainter stars were being merged with the Cepheid in Hubble's observations, the measured period luminosity relationship might be skewed, artificially inflating the inferred distances and thus the derived expansion rate. Webb, with its far superior infrared resolution, can resolve individual stars in these same galaxies with much greater clarity. The JWST team used Webb specifically to test this hypothesis in 2024 and 2025. The outcome was decisive. Webb's data matched Hubble's data. The crowding effect was real and could be measured, but its magnitude was much too small to explain the Hubble tension. When the JWST team applied the crowding correction derived from Webb's sharper images, the local Hubble constant came down by only about 1 km per second per megaparsec, far too little to bridge the 9 km per second per megaparsec gap to the Planck value. As reported across physics news outlets in late 2024, the conclusion from this analysis was unambiguous. The local expansion rate is genuinely, robustly high, and the tension with the early universe measurement is not a product of measurement error. It is a real disagreement between what the early universe predicts and what the late universe delivers. At a meeting of the American Astronomical Society in January 2025, Dan Skolnick of Duke University, one of the world's foremost experts on Type Ia supernovae and cosmological distance measurements, stood before his colleagues and declared plainly that the Hubble tension is now a crisis. Not a discrepancy, not a tension awaiting resolution, but a crisis that demands new physics. The Tensions in Cosmology, 2025 conference in Corfu, Greece, which brought together over 130 researchers working at the frontier of this problem, concluded that the Hubble constant discrepancy has now reached a statistical significance exceeding 6 sigma, meaning that the probability of this disagreement arising by chance within the standard model is astronomically small, less than 1 in a billion. The conference identified the Hubble tension as the single most pressing unresolved problem in fundamental physics. And here is why all of this matters for the structures we have been discussing throughout this episode. The Hubble constant is not just a number about the expansion rate. It is woven into the entire fabric of the standard cosmological model. It determines the age of the universe, the critical density above which the universe is geometrically closed, the scale of baryon acoustic oscillations, and the rate at which structure formation proceeded across cosmic time. If the Hubble constant is genuinely higher than the Planck-based Lambda CDM prediction, it does not just require a small adjustment. It suggests that something is fundamentally wrong with either the early universe measurement, the late universe measurement, or the model that is supposed to connect them across 13.8 billion years of cosmic evolution. One of the most discussed theoretical proposals for resolving the Hubble tension is the concept of early dark energy. In this framework, a form of dark energy existed in the early universe, before the cosmic microwave background was emitted that briefly boosted the expansion rate above what the standard cosmological constant would produce. This would alter the acoustic scale of the early universe and, if calibrated correctly, could bring the CMB-based Hubble constant prediction into agreement with the locally measured value. A study published in the monthly notices of the Royal Astronomical Society in 2024 by Xuejian Shen of MIT and colleagues, including Sandro Tacella and Michael Boylan-Kolchin, explored whether this same early dark energy framework could simultaneously explain both the Hubble tension and the excess of bright, massive early galaxies that Webb has revealed. Their analysis found that an early dark energy cosmology could accommodate a significant fraction of the tension between the Webb galaxy data and standard Lambda CDM. But early dark energy is a theoretical construction that introduces new degrees of freedom into the model. It requires a new field with specific properties that have not been independently detected, and crucially, it is not the only proposal on the table. Other researchers have explored modifications to the late universe dark energy, changes to the matter radiation equality epoch, exotic dark matter candidates, primordial black holes as galaxy formation seeds, and a variety of other mechanisms, none of which has yet achieved consensus support. The theoretical landscape at this moment in cosmology is extraordinarily fertile and genuinely unsettled. What is clear, as we step back and survey everything that Webb has brought into focus alongside the parallel discoveries from ground-based surveys, is that the universe appears to be more complex, more structured on large scales, and more rapidly evolved in its early history than the standard model predicted. Whether the ultimate resolution lies in a modification of inflation, a revision to dark energy, a reconsideration of the cosmological principle, or something entirely new that nobody has yet formulated, remains the great open question of 21st century cosmology. To understand just how interconnected these threads are, it helps to look at what cosmologists call the cosmic web in closer detail, and to ask what the web should look like versus what Webb and its companion surveys are actually finding. The cosmic web is not a metaphor, it is a structure, a real three-dimensional architecture of matter distributed across hundreds of millions and billions of light-years, and it is one of the most visually and conceptually striking features of the observable universe. At the nodes of the web sit the most massive galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies, embedded in enormous halos of dark matter and hot X-ray emitting gas. Connecting these nodes are the filaments, elongated streams of galaxies and gas stretched across tens and hundreds of millions of light-years. Between the filaments are the voids, regions so empty of galaxies that they challenge the imagination, volumes of space tens of millions of light-years across containing almost nothing. The cosmic web was predicted before it was observed. Numerical simulations of structure formation in Lambda CDM, beginning in earnest in the 1980s and achieving extraordinary sophistication by the 2010s, generated synthetic universes whose large-scale structure bore a striking resemblance to what sky surveys were revealing. This was one of the great triumphs of the standard model. The Millennium Simulation, published in 2005 by Volker Springel and a large international collaboration, modelled the gravitational evolution of more than 10 billion dark matter particles from the early universe to the present day, and the resulting synthetic universe displayed precisely the kind of filamentary, web-like structure that galaxy surveys were cataloguing in 3 dimensions. The match was not perfect in every detail, but it was impressive enough to give cosmologists genuine confidence that Lambda CDM captured the essential physics of how matter organizes itself across cosmic scales. But here is what those simulations consistently showed, and what the theoretical framework consistently predicted. The web, for all its visual complexity, should smooth out on the very largest scales. Go far enough above the level of individual filaments and clusters, zoom out to a scale of hundreds of millions or billions of light-years, and the distribution of matter should begin to look uniform. Individual structures, no matter how large they appear at smaller scales, should fade into statistical insignificance when you average over large enough volumes. The principle is not that there are no structures. Of course there are. The cosmic web is full of them. The principle is that no single structure should dominate the landscape above the theoretical size limit. What Webb is showing us, in concert with ground-based surveys and analyses like those of Lopez and Horvath, is that the landscape at the larger scales is not as smooth as predicted. Structures are appearing in the data that are too large, too coherent, too geometrically organized, and too early in cosmic time to fit comfortably within the standard framework. And when you combine this with the Hubble tension, and with the anomalously massive and luminous early galaxies, what emerges is not a collection of isolated puzzles, but a pattern, a consistent direction in which the data diverges from the model. The universe appears to have formed structure more quickly, in denser configurations, and on larger scales than Lambda CDM predicts. Now, there are scientists who argue that this pattern is not as significant as it appears, and their arguments deserve to be heard. Some point out that our observable universe is just one realization of the cosmos, and that statistical fluctuations in structure formation could, in principle, produce the structures we observe even within Lambda CDM, just with very low probability. The question of whether a structure is truly incompatible with the standard model, or merely very unlikely within it, is a nuanced one, and the answer depends heavily on how precisely the structure's properties can be measured. Others argue that the theoretical size limit of 1.2 billion light-years is not as hard a boundary as it is sometimes presented, that it represents a scale beyond which structures become statistically improbable rather than physically impossible, and that the precise threshold depends on the cosmological parameters assumed in the calculation. These are legitimate points. Cosmology is not a field in which results should be accepted uncritically, and I think it is worth being candid about this. As this channel has always tried to demonstrate, the most useful thing we can do is to honestly present what the evidence shows, acknowledge what remains uncertain, and encourage the kind of independent thinking and research that keeps science honest. The crisis in cosmology is real, in the sense that serious researchers are using that word to describe it. But a crisis in science is not the same as a failure of science. Crises are how science grows. They are the moments when the frontier expands, when the territory of the unknown is revealed, when the next generation of ideas begins to take shape. And the ideas taking shape right now are genuinely fascinating. One of the most discussed possibilities in the theoretical community is that dark energy, the mysterious component making up approximately 68% of the total energy content of the universe and responsible for the accelerating expansion first discovered in 1998 by Saul Perlmutter, Brian Schmidt and Adam Rees, may not be the simple cosmological constant that Lambda CDM assumes. Einstein introduced the cosmological constant, which he called lambda, as a term in his field equations of general relativity to represent the energy of empty space, a constant, unchanging contribution to the universe's expansion. The discovery in 1998 that the universe's expansion is accelerating resurrected this idea and gave it a physical interpretation. But if lambda is truly constant, if the energy of the vacuum is truly fixed and invariable across all of space and time, then certain relationships between cosmological parameters should hold precisely, and they do not. The Dark Energy Spectroscopic Instrument, or DESI, a massive galaxy survey instrument mounted on the Mail telescope at Kitt Peak National Observatory in Arizona, has been mapping the three-dimensional distribution of tens of millions of galaxies to measure the baryon acoustic oscillation scale across different epochs of cosmic history. Its results, released in 2024 and updated in 2025, provided intriguing hints that dark energy may have evolved over time. A WCDM analysis using the DSI data, which allows the dark energy equation of state to deviate from the cosmological constant value of -1, found a mild but suggestive preference for dynamical dark energy. This result, while not yet statistically decisive, points in the same direction as other anomalies. It suggests that the universe's expansion history may be more complex than the simplest Lambda CDM model allows. The sign-switching cosmological constant scenario, sometimes called Lambda sub SCDM, has been an active area of theoretical development in 2025. In this framework, the cosmological constant changed sign at a redshift of approximately 1.7, transitioning from a repulsive to an attractive influence before returning to a repulsive one. This exotic-sounding idea was explored at the Tensions in Cosmology 2025 conference in Corfu, where researchers found that it showed promising potential to simultaneously address both the Hubble tension and the S8 tension, which is a separate but related discrepancy between the predicted and observed amplitude of matter clustering in the late universe. The Corfu conference report, compiled by an international team and published in Nature Astronomy, described this and several related ideas as among the most viable directions for theoretical development in the face of the accumulating observational anomalies. There is also growing interest in the possibility that the solution lies not in dark energy, but in dark matter, the invisible component comprising roughly 27% of the universe's energy content and providing the gravitational scaffolding for galaxy formation. Standard Lambda CDM assumes that dark matter is cold, meaning its constituent particles were moving slowly compared to the speed of light when the universe was young, which favours the formation of small structures first that later merge into larger ones. But there are alternatives. Warm dark matter, whose particles move faster, would suppress the formation of the very smallest structures and alter the abundance of dwarf galaxies. Fuzzy dark matter, proposed as an extremely light quantum particle whose wave nature imprints itself on cosmic scales, would smooth out structure formation below a certain length scale in ways that might relieve some of the small-scale tensions in Lambda CDM. Primordial black holes, hypothetical black holes that formed from density fluctuations in the very early universe, rather than from stellar collapse, have been proposed as dark matter candidates and as seeds that could accelerate the early formation of massive galaxies like those Webb is finding. None of these alternatives has been definitively confirmed. None has produced a single coherent framework that resolves all of the tensions simultaneously. But the number and variety of serious proposals being explored in the peer-reviewed literature is itself a signal of how deep the current questions go. And at the centre of all of this, returning us to where this episode began, is the James Webb Space Telescope. Webb did not create these problems. It did not introduce errors or artifacts that produce false anomalies. The structures being studied with ground-based surveys like the Sloan Digital Sky Survey were found before Webb launched. The Hubble tension was identified long before Webb flew, but Webb has sharpened the picture in ways that are, if anything, making the tensions more acute rather than less. Its sensitivity to the infrared universe has allowed spectroscopic confirmation of early galaxies at redshifts that were previously only photometric estimates. Its resolution has ruled out instrumental artifacts in the Cepheid distance ladder, and its ongoing deep surveys are continuing to reveal the high redshift universe in unprecedented detail, generating new data that theorists are actively racing to explain. In May 2025, Webb detected a galaxy called MOM-Z14, with a redshift of 14.44, surpassing even JADES-GS-Z14-0 as the most distant confirmed galaxy ever observed. The cosmos keeps offering up these records not as isolated curiosities, but as data points in an accumulating argument that the early universe was more productive, more structured, and more chemically advanced than any model constructed before Webb flew. Each new, most distant galaxy, each new confirmed massive early system, each new structural anomaly maps out the territory more clearly and narrows the space in which purely conventional explanations can operate. What does all of this mean in plain language? It means that the universe, the actual universe in which we live, appears to be more complex, more rapidly evolving, and more structurally organized at large scales than the model we've been using to describe it for the past several decades. That model, Lambda CDM, remains one of the most successful theories in the history of science. It is not wrong in the sense of being randomly or wildly inaccurate. It is wrong, or at minimum incomplete, in specific, consistent, and increasingly well-characterized ways that point toward new physics waiting to be discovered. The structure that James Webb spotted, the structure that according to our best models should not exist, is not just a single object. It is a population of objects, a pattern of observations, a body of evidence that together tells a story about a universe that formed its first great works, faster, larger, and more elaborately than we gave it credit for. And the fact that we can now see this, that we can now measure it and debate it and build theories around it, is itself one of the most remarkable achievements in the history of human inquiry. I also want to take a moment here to say something that I think is genuinely important, and which reflects how I think about the role this channel plays. We are living through a real scientific revolution in real time. The publications, the conference proceedings, the preprints, the peer-reviewed papers that form the foundation of everything we have discussed today, they are not hidden behind paywalls of specialized knowledge. They are accessible. They are readable. Many of the key researchers involved, from the JWST team to Alexia Lopez to the SHOES collaboration to the scientists at the Tensions in Cosmology conference, have made their work available not only in formal journals but through preprint servers like Arxiv, where anyone in the world can read the raw scientific arguments without a subscription fee. I genuinely encourage you to take advantage of that. Look up JADES-GS-Z14-0. Read Boylan-Kolchin's stress test of Lambda CDM. Look at Lopez's papers on the giant arc and the big ring. Form your own sense of the evidence. Challenge what I have told you. Look for the counterarguments. That is how good scientific thinking works, and this community is at its best when we engage with evidence together rather than simply accepting any single narrative, including mine. Because the truth is that nobody knows yet exactly what these observations mean for the future of cosmology. The crisis is real, the anomalies are real, and the need for new ideas is real. But the resolution could come in many forms. It could come through a revision to inflation, the epoch that seeded all structure in the cosmos. It could come through new understanding of dark energy or dark matter. It could come through a discovery that some of the larger structures have been misidentified through observational artifacts that only much larger and more complete surveys will clarify. Or it could come through something entirely new, a physical principle or mechanism that nobody has yet imagined. One that will make future generations look back at this moment the way we look back at the early days of quantum mechanics or general relativity, when the old framework was strained to its limits, and something genuinely transformative was waiting just beyond the horizon of the known. And that open question is exactly where we find ourselves now, poised at the edge of what we know, looking out into the vastness of what Webb continues to reveal. Because the structures and the galaxies we have discussed so far, as extraordinary as they are, represent only part of what this telescope is showing us. There are deeper layers to this mystery. There are findings that connect the early universe anomalies to the present-day structure of the cosmos in ways that suggest the whole framework may need rethinking from the ground up. And there are theoretical ideas being actively developed right now by brilliant and careful scientists working at universities and observatories around the world that could, if confirmed, transform our understanding of everything from the beginning of time to the ultimate fate of the universe. There is a galaxy called GN-Z11, and it has become one of the most discussed objects in contemporary astrophysics for reasons that cut directly to the heart of everything we explored in Part 1. GN-Z11 sits at a redshift of 10.6, meaning its light has been travelling toward us for roughly 13.4 billion years, placing it at a cosmic epoch when the universe was only about 430 million years old. It was first identified by the Hubble Space Telescope and was for years considered one of the most distant objects in the observable universe. But when Webb turned its infrared eyes on GN-Z11 in early 2023, devoting more than 10 hours of spectroscopic observation to it, the resulting data revealed something that genuinely stunned the researchers who analysed it. At the centre of GN-Z11, Webb detected the unmistakable spectroscopic fingerprints of an active, accreting supermassive black hole. The galaxy itself is compact, roughly 100 times smaller in physical extent than the Milky Way, but the black hole at its core appeared to be extraordinarily massive for such a young system, and it appeared to be consuming gas at a prodigious rate, possibly at what physicists call super-Eddington accretion, meaning it was swallowing matter even faster than the theoretical maximum rate set by the balance between gravitational pull and radiation pressure. Roberto Maiolino of the University of Cambridge, who led the team that published these findings in Nature, described the moment of discovery as among the most exciting in his career. He said that the sensitivity leap provided by Webb compared to previous telescopes was like upgrading from Galileo's first telescope to a modern observatory overnight. The spectrum that Webb obtained was technically decisive. It showed specific emission lines, including the NE4 doublet at 2,423 angstroms and CII star at 1,335 angstroms, which are characteristic of active galactic nuclei powered by a central accreting black hole. Additionally, the spectrum contains semi-forbidden nebular lines indicating gas densities greater than 10 to the 9th power particles per cubic centimetre, a density that is characteristic of the broadline region immediately surrounding a feeding black hole. These signatures were unambiguous. GN-Z11 contained a vigorously feeding supermassive black hole when the universe was less than 500 million years old, a conclusion that researchers found profoundly challenging to accommodate within conventional black hole formation models. Because the problem is not just that such a black hole exists, the problem is that it exists already. Black holes form and grow over time, they need matter to accrete and mergers to accelerate their growth, and the universe, at a redshift of 10.6 had simply not been around long enough for conventional growth processes to produce what Webb was seeing. GN-Z11 is not an isolated case. The problem of overmassive black holes in the early universe is one that Webb has been relentlessly deepening with each new survey campaign. Observations of galaxy populations at redshifts greater than 4, corresponding to the first roughly 1.5 billion years of cosmic history, have revealed that the central black holes in those systems are, in many cases, between 10 and 100 times more massive relative to their host galaxies than would be expected from the scaling relations established in the nearby universe. In the local cosmos, there exists a remarkably tight correlation between the mass of a galaxy's central supermassive black hole and the total stellar mass of that galaxy's central bulge. This relationship, known as the M-sigma relation, is interpreted as a fundamental signature of coevolution. Black holes and galaxies growing together through a shared history of gas accretion and stellar feedback, each regulating the other's development through the energy released during intense episodes of activity. If early universe black holes are already 10 to 100 times more massive relative to their host galaxies than this relationship permits, it means either that black holes obtained a dramatic head start that the surrounding stellar populations have not yet caught up to, or that the coevolution relationship itself does not hold in the first billion years of the universe, or that the standard picture of how both grew in tandem is missing something fundamentally important. Fabio Pacucci of the Center for Astrophysics at Harvard and the Smithsonian, one of the most active researchers on early universe black holes, led a team whose analysis of a population of small early galaxies from JWST data found that in a significant fraction of cases the central black hole was substantially more massive than the M-sigma relation would predict. Pacucci proposed that the explanation may lie in the black holes growing first, accumulating mass before their host galaxies had built up significant stellar populations. But this proposal, while coherent in itself, raises a further question. How did those black holes grow so fast to begin with, given that even the most generous conventional accretion models struggle to produce billion solar mass black holes within the first few 100 million years, unless the seeds were unusually massive or the accretion unusually rapid? CONSPI-2 equals a 2025 paper examining observational biases in early black hole measurements offered a partial resolution to the tension. The team argued that the most luminous, most easily detected systems at high redshift are precisely those where a vigorously feeding black hole is temporarily outshining its host galaxy, skewing the measured black hole to stellar mass ratio toward extreme values. Correcting for this selection effect brought some of the most apparent outliers back toward consistency with the local scaling relation. But a genuinely overmassive population appeared to remain even after the correction, and the fundamental question of black hole seed formation was not resolved by this accounting. That question connects to one of the most fascinating unresolved debates in astrophysics: the nature of the first black holes ever to form in the universe. In the standard stellar evolution picture, black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. The very first generation of stars, known to astronomers as population 3 stars, formed from pristine primordial gas containing only hydrogen and helium, with trace amounts of lithium, with no heavier elements at all. Because metals are crucial for cooling and fragmenting gas clouds into small clumps, the absence of metals in the primordial gas meant population 3 stars could grow to extraordinary masses, perhaps hundreds of times the mass of the Sun. When these first stars died, they would have left behind black holes of perhaps tens to hundreds of solar masses, what theorists call light seeds. For light seeds to become the billion solar mass behemoths that Webb is detecting at redshift 10 and beyond, they would need to grow by roughly 7 to 8 orders of magnitude in a few 100 million years, a challenge that requires either continuous highly efficient gas accretion or enormous numbers of mergers, and standard models strain under this demand. The alternative is a class of objects called direct collapse black holes, or heavy seeds, formed not from stellar death but from the monolithic gravitational collapse of a massive cloud of primordial gas, with a mass of perhaps 10,000 to 100,000 solar masses, bypassing the stellar phase entirely and providing a much more massive starting point. Theoretical models have established that direct collapse is physically plausible under specific and rare conditions: dense primordial gas, suppressed molecular cooling that prevents fragmentation into stars, and intense radiation fields in the surrounding environment from nearby young galaxies. These conditions could have been met in particular environments where the geometry and mass ratios of neighbouring dark matter halos converged to produce a pristine, unfragmented gas cloud of extraordinary density. From such a collapse, a black hole seed 10,000 or more times more massive than a stellar remnant would emerge, giving the subsequent growth process a head start that makes the observed high redshift masses far more achievable. Webb's exploration of possible direct collapse candidates, including a system described in 2025 reporting as a potential direct collapse black hole, based on spectral features inconsistent with a stellar origin, represents one of the most exciting frontiers in current observational astrophysics. These objects would be extraordinarily rare in any given epoch, existing in only the most unusual environments of the early universe, but their existence, if confirmed, would close one of the most persistent gaps in the theory of how the universe went from a smooth distribution of hydrogen and helium to the complex structured cosmos we inhabit today. Now let us address one of the most theoretically provocative dimensions of the case that Webb's data is building. It is a dimension that goes beyond adjustments within the Lambda CDM framework and into the question of whether the very foundation of the model, the assumption that cold dark matter provides the primary gravitational scaffolding for structure formation, is the most accurate description of what the universe is actually doing. Const P3 equals dark matter was not invented out of thin air. The evidence for its existence is both substantial and diverse. Galaxy rotation curves, mapping the orbital speeds of stars and gas as a function of distance from a galaxy's centre, remain stubbornly flat in the outer regions of spiral galaxies, rather than declining as Newton's gravitational law would predict for the visible mass alone. Vera Rubin and Kent Ford systematically documented this phenomenon across dozens of galaxies in the 1970s, establishing that either enormous quantities of invisible mass surrounded every spiral galaxy, or that Newtonian gravity fails in some regime of weak acceleration. Gravitational lensing, the bending of light from background objects by the gravitational field of foreground structures, independently confirms the presence of vast invisible mass in galaxy clusters that exceeds the observed stellar and gas content by factors of 5 to 10. The Bullet cluster, where two galaxy clusters collided and passed through each other roughly 150 million years ago, provides a remarkably clean demonstration. The hot gas of the colliding clusters traced through its X-ray emission was slowed by electromagnetic friction during the passage and lagged behind the collision center. Meanwhile, the invisible mass, traced through gravitational lensing of background galaxies, passed straight through without slowing, producing a clear spatial offset between the ordinary matter and the gravitating mass. This is precisely what cold dark matter particles, which interact only through gravity, would do. And the cosmic microwave background provides perhaps the most precise and independent line of evidence. The pattern of temperature fluctuations imprinted in the CMB at redshift 1100 is exquisitely sensitive to the composition of the early universe, and the Planck satellite's measurements are only consistent with a universe in which cold dark matter makes up approximately 27% of the total energy content. Fitting the CMB without dark matter produces results that are dramatically, unmistakably, statistically catastrophically worse. All of this is why Lambda CDM, despite its current tensions, retains the confidence of most of the cosmological community. Dark matter is not an ad hoc assumption. It is a convergent conclusion from multiple independent methods. But its fundamental nature, what particle or field or object actually constitutes the dark matter, remains completely unknown after more than 4 decades of searching. No laboratory experiment has directly detected a dark matter particle. No confirmed signal has emerged from decades of direct detection experiments running deep underground to shield against cosmic ray backgrounds, or from indirect detection surveys scanning the sky for the gamma rays that would result if dark matter particles annihilated each other in dense regions like the galactic center, or from accelerator experiments at the Large Hadron Collider at CERN that have probed the energy scales where the most popular dark matter candidates were predicted to be produced. The most widely studied theoretical candidate, the weakly interacting massive particle, or WIMP, has seen its allowed parameter space compressed by progressively more sensitive experiments to a tiny fraction of what it once occupied, without the particle itself materializing. It is in this context of dark matter's existence being evidentially supported but its nature being utterly unknown, that Webb's observations have given new energy to a long-standing alternative proposal, modified Newtonian dynamics. MOND was formulated in 1983 by Israeli physicist Mordechai Milgram, who proposed that Newton's second law of motion requires a modification in the regime of extremely weak gravitational accelerations, specifically below a critical acceleration of approximately 10 to the negative 10 meters per second squared. Below this threshold, Milgram argued, the relationship between force and acceleration changes, causing gravity to fall off more slowly with distance than the standard inverse square law predicts. In this modified regime, the effective gravitational force scales as 1 over the distance rather than 1 over the distance squared, which naturally reproduces the observed flat rotation curves of spiral galaxies without requiring any additional invisible mass. The theory makes specific and quantitative predictions about how the rotation speed of any galaxy should relate to its total baryonic or ordinary mass, and these predictions have been impressively confirmed across a remarkable range of galaxy types and mass scales through what is now called the radial acceleration relation. This tight empirical correlation between the centripetal acceleration of orbiting stars and gas and the gravitational acceleration predicted by the visible matter alone holds from the smallest dwarf galaxies to the most massive spirals, a uniformity that MOND predicts naturally, but that cold dark matter models struggle to explain without additional fine-tuning. In November 2024, Stacey McGaw of Case Western Reserve University published a paper in the Astrophysical Journal, co-authored with Federico Lelli of the INEA-F Arcetri Astrophysical Observatory in Italy, Jay Frank and James Schombert of the University of Oregon, arguing that MOND had made a specific falsifiable prediction more than 25 years ago about the scale and rapidity of early cosmic structure formation, and that Webb's observations are now confirming that prediction. In a 1998 paper, McGaw had argued from the logic of MOND that without cold dark matter's gradual gravitational scaffolding effect, baryonic matter in the early universe would collapse directly and rapidly under MOND's enhanced effective gravity, producing large luminous galaxies at much earlier cosmic epochs than the Lambda CDM model anticipated. The large bright galaxies at high redshift that Webb is now systematically discovering aligned with that 26-year-old prediction in a way that the cold dark matter framework did not anticipate. McGaw's public statement about this was characteristically plain. The bottom line, he said, is "I told you so." He noted that while he'd been raised to consider such a statement rude, it was precisely the point of the scientific method to make predictions and then check which ones came true. McGaw was equally candid about MOND's limitations. Finding a fully relativistic formulation of MOND that is consistent with both general relativity and the detailed properties of the cosmic microwave background and baryon acoustic oscillations remains a major unsolved theoretical challenge. MOND in its original form is a modification of Newtonian dynamics at the galaxy scale, not a complete cosmological theory, and extending it to the regime of the very early universe, where quantum gravity effects may be relevant, and where the cosmological principle is at stake, requires theoretical work that has not yet reached consensus. But the predictive success that McGaw and colleagues were pointing to was real and documented, and in the current climate of accumulating anomalies, any theoretical framework that correctly anticipated Webb's findings deserves to be taken seriously rather than dismissed. MOND and its relativistic descendants also have something important in common with the wave dark matter or fuzzy dark matter proposals that have been gaining attention from Webb's morphological observations. Both modify the behavior of gravity or matter on galactic and subgalactic scales in ways that affect the shapes and formation histories of early galaxies. A December 2025 study from Arizona State University, published in Nature Astronomy and involving researchers from MIT, Harvard, and Taiwan, examined the shapes of young galaxies observed by Webb in the JWST survey within the first 1.8 billion years after the Big Bang, and found that these galaxies displayed unexpectedly elongated prolate morphologies stretched out along one axis rather than being compact or roughly spherical. Comparing these observed shapes to simulations using cold dark matter on one hand and warm dark matter or wave dark matter on the other, the team found that the smooth, coherent filamentary structure of dark matter in the warm and wave scenarios produced elongated galaxy shapes that better matched the Webb observations, while cold dark matter's clumpy fractal filaments tended to produce more compact or irregular morphologies at these epochs. The team was careful to note that this result was suggestive rather than definitive, and that further observations and more refined simulations would be needed to establish it conclusively. but added to the other anomalies, it contributed another thread to the tapestry of evidence that something about the standard dark matter picture may need revision. Cons.P4 equals all of these individual lines of evidence, the massive early galaxies, the overmassive early black holes, the large-scale structural anomalies, the Hubble tension, the morphological signatures in early galaxy shapes, converge on a single broad conclusion that the cosmological community is now taking seriously at the highest levels. The universe, as revealed by the most sensitive instruments ever built, is not quite behaving as our best model predicts. The discrepancies are not random, and they are not small. They are systematic. They're growing more significant as the data quality improves rather than disappearing as measurement errors are reduced, and they consistently point in the same direction, toward a cosmos that formed its earlier structures faster, on larger scales, and with greater abundance than the Lambda CDM model anticipated. What can cosmology do with this? The range of theoretical responses currently under active development is itself a testament to the vitality of the field. At the conservative end, researchers are working to understand whether modifications to galaxy formation physics, without changing the underlying cosmological model, can accommodate the anomalies. Perhaps feedback from early supermassive black holes was more intense in the early universe than current simulations capture, stripping away interstellar gas and making the surviving stellar populations appear more concentrated and luminous. Perhaps the initial stellar mass function, the distribution of stellar masses at the moment of birth, was different in the early universe than it is today, producing more massive and luminous stars per unit of gas mass, and thereby amplifying the apparent brightness of early galaxies. Perhaps molecular cooling was less efficient in the low metallicity environments of the first galaxies, allowing gas to remain warmer and less fragmented, and thereby forming stars in larger, denser concentrations. All of these mechanisms are physically motivated, all are being actively incorporated into state-of-the-art simulations, and all have the potential to partially resolve some of the tensions without abandoning the fundamental framework. At the less conservative end, modifications to the cosmological model itself are under serious consideration. Early dark energy, a component of the universe's energy budget that briefly dominated before the formation of the cosmic microwave background and then decayed away, would alter the sound horizon scale of the early universe and could, if properly calibrated, bring the Planck-based Hubble constant prediction into agreement with the locally measured value. Several independent groups have explored this proposal, and it remains among the most viable explanations for the Hubble tension in the peer-reviewed literature. The challenge is that early dark energy requires a new fundamental field with specific properties and a specific temporal behavior, none of which has yet been independently confirmed, and that it must be finely tuned to produce the right amount of effect without running afoul of other cosmological constraints. Dynamical dark energy, in which the equation of state of the dark energy component varies with cosmic time rather than remaining fixed at the cosmological constant value of -1, has received increasing attention in light of the Dark Energy Spectroscopic Instruments 2024 and 2025 results. DESI's Galaxy Survey data showed a mild but suggestive preference for an evolving dark energy equation of state, a result that aligns with the overall direction of the cosmological tensions, even though its statistical significance has not yet crossed the threshold typically required to claim a discovery. The 2026 second data release from DESI, combining its full year 2 observations with improved systematic controls, was anticipated to substantially sharpen this measurement. Modifications to inflation, the hypothesized epoch of exponential expansion in the very early universe that set the initial conditions for all subsequent structure formation, offer another avenue for theoretical exploration. The simplest inflationary models predict a specific spectrum of initial density fluctuations, the so-called Harrison-Zeldovich power spectrum, that Lambda CDM inherits and uses as its starting point. But more complex inflationary scenarios can produce power spectra with excess power on specific scales, amplifying the initial seeds for structure formation in certain regimes, and potentially enabling the faster growth of large-scale structures that Webb and the ground-based surveys are revealing. While purely speculative without independent evidence for which inflationary model is correct, these proposals are theoretically coherent and represent genuine alternatives to the simplest case. And then there are the more radical proposals, those that question not just the parameters of the standard model, but its foundational architecture. Some researchers have explored whether the cosmological principle itself, The assumption that the universe is homogeneous and isotropic on the very largest scales is as accurately established as we have assumed. The growing catalogue of structures, from the giant arc to the Hercules Corona Borealis Great Wall, that appear to exceed the theoretical size limit imposed by this principle, is, at minimum, straining the empirical basis for the assumption. If the universe has a genuine large-scale texture, a directionality or preferred orientation that does not average out even on the largest observable scales, then the standard cosmological model, which assumes perfect homogeneity as its geometric foundation, would require fundamental revision. Testing this possibility requires precisely the kind of large-scale surveys that Euclid and the Nancy Grace Roman Space Telescope are being built to provide. Const P5 equals speaking of those instruments, let us trace out what the next several years will bring to this ongoing investigation. The European Space Agency's Euclid mission, operated by a consortium of more than 2,000 scientists from 300 institutions across 15 countries plus the United States, Canada, and Japan, is specifically designed to address the dark energy and structure growth questions through large-scale cosmological surveys of unprecedented scope. By March 2025, Euclid had already observed about 2,000 square degrees of sky and released a dataset covering 26 million galaxies in a single mosaic covering more than 500 times the area of the full moon. This was a preview, a demonstration of capability and data quality rather than a cosmological result. The mission's first cosmology data release, carrying the statistical power needed to make precision measurements of the dark energy equation of state, the growth rate of structure across cosmic history, and the large-scale distribution of dark matter, was planned for October 2026. Euclid's primary tools are weak gravitational lensing, the statistical measurement of subtle distortions in the shapes of background galaxies caused by the gravitational influence of all intervening matter, and galaxy clustering, particularly the baryon acoustic oscillation scale, measured in the three-dimensional distribution of millions of galaxies. The combination of these two techniques across a survey area of 14,000 square degrees, 1/3 of the entire sky, will produce a three-dimensional map of the universe's matter distribution, spanning 10 billion years of cosmic history. This map will provide the most precise measurements yet of the S8 tension, the Hubble constant, and the properties of dark energy, with a statistical precision that should be able to detect even subtle deviations from Lambda CDM. Pierre Ferrouille, ESA's Euclid mission manager, has described the telescope as the ultimate discovery machine, and when its full survey data are released over the coming years, the scientific return will be transformative for the field. NASA's Nancy Grace Roman Space Telescope was completing its final ground testing and preparation as of mid-2026, with launch planned for later that year aboard a SpaceX Falcon Heavy rocket. Named for Nancy Grace Roman, widely recognized as the mother of Hubble, for her foundational role in establishing space-based astronomical observatories at NASA in the 1960s and 1970s, the telescope carries a 2.4-meter primary mirror and a 300-megapixel wide-field instrument with a field of view 100 times larger than Hubble's, while maintaining sharpness comparable to Hubble. Roman's planned high-latitude wide-area survey will observe approximately 2,000 square degrees of sky in the infrared, measuring the shapes of hundreds of millions of galaxies for weak lensing cosmology, mapping the three-dimensional distribution of galaxies through spectroscopy, and conducting one of the most comprehensive Type 1a supernova surveys ever attempted. All of these measurements are directly targeted at the cosmological questions that are under tension from Webb's observations. China's Xuntian Space Telescope, also known as the Chinese Space Station Telescope, was being prepared for deployment from the Tiangong Space Station in 2026. With a 2-meter primary mirror, a field of view 100 times wider than Hubble, and a planned 10-year mission covering survey science in near-ultraviolet to near-infrared wavelengths, Xuntian will conduct wide-field imaging and spectroscopic surveys complementary to those of Euclid and Roman, adding substantially to the global dataset available for testing cosmological models. The coincidence of 3 major space-based cosmological survey telescopes entering operation within a few years of each other represents an extraordinary convergence of international scientific ambition and technical capability. On the ground, the Dark Energy Spectroscopic Instrument at Kitt Peak National Observatory was entering the final phase of its 5-year survey as of 2026, with a second major data release expected to provide updated and more precise measurements of baryon acoustic oscillations and redshift space distortions from 40 million extragalactic spectra. The square-kilometre array, under construction with stations in Australia and South Africa, will, when complete, add the capability for neutral hydrogen surveys that can trace the large-scale distribution of matter on the deepest scales through 21-centimetre line emission, providing yet another independent constraint on the cosmological parameters that are currently in tension. The convergence of all these instruments on the same set of cosmological questions in the same half-decade is not coincidental. It reflects a strategic recognition, built up over years of community planning, that the anomalies revealed by Webb and the ground-based surveys cannot be resolved by any single observation or any single instrument. Resolving them requires the combined statistical power of multiple independent approaches, measured across complementary wavelength ranges, probing different cosmic epochs and different physical phenomena, so that systematic errors in any one method can be identified and corrected against the others. This is the global scientific strategy for 2026 and beyond, and it is being executed by the largest and most internationally collaborative scientific program in the history of observational astronomy. CONSP6 equals, within this context of upcoming opportunity, it is worth reflecting on what exactly we're asking these instruments to decide. The choice is not simply between Lambda CDM being right or wrong. That framing is too binary for a field operating at the frontier of measurable reality. The real question is how much Lambda CDM needs to be modified, in which directions, and by what physics, to accommodate the observations that are accumulating. Every viable modification of the standard model has consequences that extend beyond the specific tension it was designed to resolve, and those consequences must themselves be tested against independent data. This is what makes the next decade of cosmology so consequential. The sheer volume and precision of the incoming data will constrain the space of viable theories more tightly than ever before, either converging on a refined and extended standard model or making the case for something genuinely new, so overwhelming that the field has no choice but to pursue it. History offers useful perspective here. When the cosmic microwave background was discovered accidentally by Arno Penzias and Robert Wilson in 1965, using a radio antenna designed for satellite communications rather than cosmological research, it confirmed the Big Bang model and transformed cosmology from a largely philosophical debate into a precision empirical science. When the accelerating expansion of the universe was announced in 1998 by the teams of Saul Perlmutter, Brian Schmidt, and Adam Rees, using observations of distant Type Ia supernovae, it overturned the then prevailing assumption that cosmic expansion should be gradually slowing down due to gravity, and required the introduction of a new component of the universe's energy budget, the cosmological constant or dark energy, that had no precedent in the standard physics of the time. Both of these transformations were deeply surprising when they occurred. Both required significant conceptual revision of the prevailing framework, and both ultimately led to a richer and more complete picture of the cosmos. The present situation bears comparison to the period just before these discoveries, when individual anomalies were beginning to cluster and accumulate without yet forming a coherent enough pattern to force a definitive revision. The Hubble tension, the massive early galaxy problem, the overmassive black hole problem, the large-scale structure violations, the morphological evidence for non-cold dark matter, the hints of dynamical dark energy from DESI, taken individually, each could perhaps be accommodated by some combination of systematic error and theoretical flexibility. Taken together, pointing consistently in the same direction, growing more robust rather than less with better data, they begin to look less like a collection of separate puzzles and more like the outline of a single coherent message from the universe. That message is not yet readable in full. The next generation of surveys will sharpen it dramatically, and the James Webb Space Telescope, still operating, still pointing its golden mirror at the most ancient light in the observable universe, will continue to add new data to the picture every single day. There is also something worth saying about the experience of living through a moment like this in the history of science. We are, all of us who follow these developments, witnesses to a genuine intellectual drama at the largest possible scale. The questions being asked are not about the behaviour of some narrow corner of physical reality. They are questions about the structure of the entire observable universe, about the nature of the two unknown substances, dark matter and dark energy, that together constitute 95% of everything that exists, about whether the mathematical framework that has guided our understanding of the cosmos for a century is the last word or merely the best word so far. These are questions whose answers, when they come, will matter not just for physics but for philosophy, for our understanding of what kind of universe we inhabit and what our place in it means. The structures that Webb and its companion observations have revealed, those rings and arcs and walls of galaxies sprawling across billions of light years, those impossibly mature early galaxies already rich in heavy elements before the universe was 250 million years old, those overmassive black holes already dominating their host galaxies before the first stars in our own galaxy had been born, are not curiosities or footnotes. They are data. They are the universe insisting, with the force of photons collected across billions of light years and processed through the most sophisticated instruments our civilization has built, that it is more complex and more astonishing than our models have given it credit for. And there is a particular kind of intellectual integrity required to receive that insistence honestly, to hold the tension between what we expected and what we observe without collapsing into either false certainty about what it means or premature dismissal of what it implies, to acknowledge that the standard model may need significant revision without catastrophizing the entire scientific enterprise, which remains one of the most powerful truth-seeking methods ever developed, to resist the temptation to dress up genuine scientific uncertainty in the language of definitive discovery, while also resisting the opposite temptation to dismiss genuine anomalies as noise. This is the posture that the best scientists working on these questions are maintaining, and it is the posture that I try to model for this channel in everything we cover. I want to be transparent with you. There is still enormous uncertainty about what these observations ultimately mean. The anomalies are real. Their interpretation is not fully settled. The theoretical landscape is broad and contested. The resolution may be a decade or more away. That is not a failure of science. That is what science at the frontier actually looks like. If you have been thinking along with me through this episode, then you have covered an extraordinary amount of ground. You have understood why the cosmological principle matters and what it means for structures to violate it. You have learned about JWST-GS-Z 14-0, the most distant confirmed galaxy ever observed, existing less than 300 million years after the Big Bang, already large and bright and chemically mature in ways that standard models struggle to explain. You have followed the story of the little red dots, those enigmatic compact red objects in the early universe that have defied classification and sparked one of the most active debates in contemporary astrophysics. You have heard about the giant arc and the big ring, two enormous structures at the same cosmic distance in the same region of sky, both violating the theoretical size limit, both without a convincing explanation within current cosmological models. You have traced the Hercules Corona Borealis Great Wall, possibly the largest structure in the observable universe, spanning 15 billion light-years and straining the cosmological principle to its breaking point. You have understood the Hubble tension as a genuine crisis that independent observations with Webb have confirmed rather than resolved, and you have followed the story of GN-Z11, where a supermassive black hole was already fully feeding when the universe was barely 500 million years old. All of these things exist. All of them are documented in peer-reviewed literature by researchers at leading institutions around the world. All of them are part of the same emerging picture of a universe that formed its structure faster, on larger scales, and with greater abundance than our best current model predicted. And all of them point toward the same conclusion, that the model, as extraordinary and successful as it has been, is not the final word on the nature of the cosmos. Something is out there, woven into the fabric of space on scales of billions of light years, structured in ways that should not exist according to the physics we thought we understood. A ring of galaxy clusters nearly perfectly circular, spanning 1.3 billion light-years, an arc of matter nearly 3 times the theoretical maximum, walls of galaxies 10 to 15 billion light-years across, galaxies bright with heavy elements and billions of solar masses of stars assembled in the first 300 million years, supermassive black holes already hundreds of millions of solar masses in size, blazing as quasars in a universe not yet 500 million years old. These are not anomalies to be wished away. They are data, and data, in the end, always wins. I want to close with something genuine. The project of understanding the universe is one of the most enduring and most human things we have ever undertaken. From the moment our ancestors first looked up at the night sky and wondered what those lights were, to the moment Webb transmitted its first infrared images of galaxies from the edge of observable time, that project has been driven by a quality of mind that no other enterprise quite captures. The combination of rigorous skepticism and genuine wonder, the willingness to be astonished and the discipline to verify, the humility to acknowledge what we do not know, and the determination to find out. Whatever the next chapter of cosmology holds, whether it is a refined and extended Lambda CDM, or a modification of gravity, or a new understanding of dark matter and dark energy, or something none of us have yet imagined, it will be found by following the data with exactly that combination of qualities. And the data is now better than it has ever been. The instruments are now more powerful than they have ever been, and the community of scientists working on these questions is larger, more globally collaborative, and more intellectually diverse than at any previous point in history. I encourage you, as I always have, to follow this story yourself. Look at the papers, read the results, engage with the scientists who are doing this work. Many of them blog, post on social media, give public talks, and write accessible explanations of their findings. The universe is not a closed book held by specialists. It is a shared inheritance and a shared mystery, and the conversation about it belongs to everyone. Check what I have told you today against what the primary sources say. Push back on anything that seems uncertain or overstated. That critical engagement is not disrespectful to the scientists whose work we have covered. It is the deepest form of respect for the scientific process itself. This is deep space intelligence. I am Liam. Thank you for being here. We will see you in the next one.